the velocity is 1.57 meter. Velocity 1.57 meter, and on this one, on 1 meter, velocity is exactly double. Then I realized this will travel exactly 4 times more according to the kinetic energy formula. See, this is 1 meter, so exactly the same amount of time it travels 4 times. So if I divide this 1.57 meter, which is one side like this, divided by 3.925, it comes exactly 4 times. So kinetic energy works perfectly on 1 meter because the velocity is squared here, or doubled, no, sorry, because the velocity is doubled here, and the kinetic energy is squared. And we can see on this one is 4 meters. This is the same way. The velocity is twice as much here, see? We can see velocity is 6.28 compared to 1 meter is exactly double, but the kinetic energy is 4 times. So it works perfectly with the pendulum as well. Even in my ramp A and ramp B, you can see when my ramp A, after 4 seconds, which is 4 meter, if I divide this by 25 centimeters in 1 second, see, kinetic energy is 16 times. So it travels 16 times more because of gained kinetic energy. So is my ramp B. See, if I divide this 4 seconds divided by 50 centimeters, comes exactly 16 times. So no matter what, this kinetic energy is playing a very important role how far the balls will be propelled, or how far the steel balls will be propelled. I have to explain a little bit about the velocity, acceleration, inertial mass, and gravitational mass. These are so important concepts, sometimes the students mix them together. But it's so important to know exactly what the velocity is, what the acceleration is, what the gravitational mass is, what the inertial mass is. And later I will explain what my experiment for Albert Einstein general relativity, especially the principle of equivalence, I made my own special pendulum to show that gravitational mass and the inertial mass in space are proportional to one another or each other. Well, of course, I will explain that later. Velocity is the change in position, but the acceleration is the rate of change of the velocity. And it's so important to know what the mass and the weights are. Mass is the quantity of the matter in a body measured by its inertia. Well, of course, later I have to explain exactly what the inertia is. Mass determines the acceleration produced in a body by a given force acting on it. The mass also determines the force exerted on a body by a gravity on Earth. Weight is a measure of how hard gravity pulls on object, or how hard is force acting on an object. Well, of course, it has to do with the local gravity, and like I explained before, on Mars it's different. 1 kilogram will be much lighter on Mars compared to Earth, and then it will be much more heavier in Jupiter. If I drop them, they will fall together. here, you cannot distinguish which one has more kinetic energy, or better word, how much work they can do. They fall together. Even, if I throw them up, they will rise together. And that is amazing. It's going against the force of gravity. I will explain that in a minute. I will demonstrate in a minute. So let's say this is 2 kilograms and this is 4 kilograms, and they have the exactly same shape and same sizes, and there is no way to distinguish which one has more kinetic energy or which one gains more kinetic energy. It doesn't matter how long they fall. So they fall together, but the important fact is when I have a soft clay underneath, or even I have something like flour, and then the 4 kilograms will penetrate more, or 4 times more, or compared to the 2 kilograms. The reason why is gaining kinetic energy. If I have this 1.5 kilogram on the floor, you see this has an inertial mass because 100% of the weight or the mass is supported by the earth. So that's the reason why this 1.5 kilogram is not suspended in air or it's not flying in space. So you can see I need force to accelerate this. So when I go back and forth, it's so easy to roll this back and forth. It's got inertial mass. But when I pick this up, see, that's different. I need a lot of force. I need exactly 1.5 kilogram force in the opposite direction to go against the force of gravity to push me. But imagine if I'm in space, I'm an astronaut, the same thing happened. Whether you have an inertial mass like astronaut in space, or like me on Earth, I have a gravitational mass. The Earth is pushing on me. In both cases, you have to accelerate. See, like this is a scale, electronic scale. I'm exactly doing the same thing. What I'm doing here, I am measuring the acceleration. If I have this 1.5 kilogram on Earth it's going to be 1.5 kilogram because I'm measuring the acceleration. This is not going to go further because Earth is pushing on a scale and the scale is pushing on this crystal ball, so they cancel each other. So you see how important it is that the mass, it depends on how hard or how fast it accelerates. So mass on Earth, like 1 kilogram is 1 kilogram. But imagine when you go on Moon, it's going to be much less. It's because of less acceleration. When you go on Mars, it's going to be 1/3 of Earth almost. When you go on Jupiter, it's going to be 2.4 kilograms. So it all depends on how mass is accelerated or how fast it's accelerated and how much momentum it gets. These are the pendulums I was talking about. See, I made the length 25 centimeters, 50 centimeters, and 1 meter. Like I said, I had also 4 meters because I can't do it over here in my lab. I had to do it in a big warehouse. But the reason why I did this, I just wanted to demonstrate that when I have 72 grams versus 36 grams, and then when I release them from 90 degrees, they fall together. But this is much different than a ramp because the friction is much less, so I had to use real good computer ball bearings. They're extremely fine and real looped and they're low friction. When I release them, what happened after a minute or two, they go out of synchronization. Even though the velocity on both are exactly the same. Because pendulum is an amazing device. Well, of course, Galileo did it, Miss Amélie de Châtelet did it, and then the most important one is Christian Huygens. He scientist, then he discovered that this can be used like a clock. The reason why, it's a harmonic oscillator. And even though it's mechanical, but it is amazing. Everything works so fine. So the amplitude, how far it travels, is exactly the same. So regardless of the mass, if I have 10 grams, 20 grams, or 200 grams, the amplitudes are the same. And this is my stopwatch. It's a perfect one. It's just precision is so good. It's 100 of a second. So this one was the one I used for the pendulum. I used for the ramps or my inclined plane, and then it worked really fine. Now, I raised this exactly 90 degrees. It's exactly, then I release it simultaneously. You see, they fall together, but see what happened. After few, you can see, if you pay attention, you can see that 72 is traveling more, even though the velocity is exactly the same. I mean, this is perfect. So it goes back and forth 1 pi, and 2 pi makes it exactly 1 second. But you can see now the 36 is slowing down, but see, 72 is going to almost 45 degrees, but 30 is going less. You can see, and after a few minutes, this is going to stop completely. But the 72 is going to keep swinging, even though the velocity is the same. But according to the kinetic energy, Ke is equal to half of mass times velocity squared. This gains more kinetic energy, so it propels itself more. These are the 3 pendulums I made. That one is 25 centimeter, 50 centimeters, and 1 meter. As you can see, if I release them, see, 25 goes much faster, and then 1 meter is going to go slower. Look. See? So 25 centimeters travel like 90 degrees or 1 pi, exactly 1 point. It travels 39.25 centimeters and 39.25 centimeters. So 25 centimeters is exactly velocity is 1.57 meters. 50 centimeters is 2.24 meters per second, and 100 centimeters is 3.14 meters per second. But also, the kinetic energy works exactly perfectly, exactly like the ramp works perfectly on this. See, on 25 centimeters, you can see pendulum, the velocity is 1.57. On 1 meter, the velocity is doubled. So in other words, if I divide this 1.57 to 39.25, it gets 4 times. So you can see I double the velocity and my kinetic energy is 4 times more. I have to mention something important here. One of the greatest minds in the history of science was Foucault. He was in France in 1851. Well, of course, he was not a physicist. He was just an experimentalist. What he did, one important experiment that changed the world, Earth's rotation. So this is the focus pendulum. So I had to scrutinize it very carefully. So I did all these calculations, and then I realized focus pendulum, when it takes exactly half a pi or 90 degrees, it takes exactly 105 meters to travel here and 105 meters to travel here. And imagine, focus pendulum was one of the greatest breakthroughs in science. The length was 67 meters and the bob was 28 kilograms, which is so massive. And the period was 16 seconds, so 8 seconds and 8 seconds back and forth. But something important that I have to mention here. On Earth, let's say the acceleration is 9.81 meter per second square. So in 4 seconds, if I drop a ball on Earth, it will be 78.4 meters per second. But on focused pendulum is more. How could it be possible? It is exceeding the acceleration due to gravity on Jupiter. How could that happen? So you can see the determining factor here is the gain kinetic energy. So that ball or that 28 kilograms focused pendulum will travel from here to here, and it takes exactly 105 meters in 4 seconds. If I divide that 105 meter by 4 seconds, I'm getting 26.25 meters, which is exceeding the Jupiter's gravity. Isn't that amazing or remarkable? So you can see always the kinetic energy comes in equation. And even though the gravity here is 9.8, and in Paris was 9.8, exactly like the way we're in Denver, and it doesn't make any difference anywhere. But how come it's exceeding not only the Earth's gravity, but also is exceeding the Jupiter's gravity? I have to mention something important. The kinetic energy of a rolling steel ball without slipping is so as you can see here, the kinetic energy of rolling ball without slipping is the kinetic energy or translational kinetic energy plus the rotational kinetic energy. But as you can see here, that I is the moment of inertia. And then when I calculated so many times precisely, I realized my rolling balls on a ramp, I don't even have to consider this rotational kinetic energy because it comes extremely small number. Even if I add this up, it doesn't make sense. So my emphasis was on this kinetic energy, which is the translational kinetic energy. The best example is when I calculated for 36 grams, the I, moment of inertia was 72 grams We've never seen that before. Even in Hadron Collider, when the protons are collided together, it's almost speed of light, almost. It's never there. So I'm using only Newtonian's mechanic, but whenever we reach the closest to the speed of light, that is going to be new. They call it relativistic kinetic energy, which is relativistic kinetic energy. In fact, the relativistic is so you can see it's the combination of Albert Einstein formula